Okay, here we go with 2025 free response questions. Question 4. Uniform disk and ring, cool, of mass m and radius r, roll without slipping, nice along a horizontal surface as shown in figure 1. Outer edges are made of the same material, center of mass, and initially move at the same constant speed v, moving at the same speed. The disk and the ring smoothly transition to a ramp. It's inclined at an angle. Both the disk and the ring continue to roll without slipping as they move up the ramp. The ring travels a greater distance along the ramp than the disk travels before. Okay, so the ring travels a greater distance along the ramp than the disk travels before each comes to a rest. We know that's going to be the case because this one's got more energy than this one because it has a more moment of inertia. So remember, when we have k rotational, that's 1/2 I omega squared. And they both have the same omega because they're both rolling at the same speed and they have the same radius. So since this one has a bigger moment of inertia, it has more energy when it's down here, which means it's going to go up the ramp higher. So I'm expecting some kind of energy question here, but we'll see. What we're hoping for is it's not a forces question, but then of course we find out it sort of is a forces question, but let's see. While the disk and the ring are rolling up the ramp without slipping, the magnitudes of the static frictional force exerted on the disk and on the ring by the ramp, friction disk, friction ramp, indicate whether the friction on the disk is greater than, less than, or equal to the friction on the ramp by writing one of the following. Boom, boom, boom. Justify your answers beyond referencing equations. So you got to justify this. So this is a little bit of a tricky question. When I was looking at it, I had to think about it for a while. So we already established that the ring is going to go up higher than the disk just because of energy right there. So since the ring goes up higher, it's going to have less net force on it. If we just, I said, I hate to go to forces, but if we just think about forces, we just have these two objects and they're going up a ramp. And if one goes up higher than the other, they start out with the same speed. So think about a block. Block's moving at one speed v. What's going to control how high this block goes compared to how high this block goes? Well, this one's going to have less friction on it than this one, more or less. But it's a little bit tricky because if we think about a block with friction going down, we're going to get a little bit misled. And that's where I started to make mistakes. Because it turns out that when we have an object like this that's rolling up the ramp, the friction force is actually, and this is very strange, actually going this way. Why is the friction force? So there's the friction on the ring, and then there's the friction on the disk. So why is the friction force going up this way? It's interesting to think about, but if we have a ring right here and it's moving at a particular speed omega like this, as it's going up the ramp, it's going to have to lose speed. So as it's going up the ramp, I'm going to switch colors right here. We're going to have to get a slower speed. So what we need is we need an angular acceleration in this direction. So once again, we have some speed omega here, and then up here, that omega is gone. So we had to lose some speed. We had to make our velocity go from something to 0. And if that happens, the acceleration has to be in the direction opposite to the velocity. And if the acceleration is in this direction, if we look at all the torques that are acting on these things, so here's my ring. I've got a gravity force going down this way. That's not going to provide any torque because it's going through the center. I've got to have something going around in this direction to find some sort of torque. So if there's an acceleration in this direction, I need a torque in this direction. And the torque in this direction is going to be friction. So as we're going up the ramp, it's not down here. As we're going up the ramp, it's not important down here. The torques are going this way and they're being provided by the friction. So this situation here is a little bit misleading, and that's where I got stuck on this problem. So it turns out if we really look at the disk going up the ramp, so there's going up the ramp, there's the disk, I can have my mg going down. If I break that up, I'm going to have an mg sine theta this way, and I'm going to have a friction on the disk going this way. So my net force for the disk has to be less than my net force for the ring. Once again, here's my net force right here is going to be mg sine theta, and I'm going to do minus the friction on the disk. That has to be less than mg sine theta minus the friction on the ring, which means that this one has to be bigger than this one. So my ring friction has to be bigger than my disk friction. Boom. So if you're going to justify your answer, you could say need more torque on disk, therefore need how are we going to phrase this? That's tricky when they say justify. So we need, it's not that we need more torque on the disk. That's not what's happening here. So don't do that. So what do we need here? We need the net force. Okay, so net force on disk needs to be smaller. So FD is bigger. And then you can reference some of the things that you're doing over here. So I think that's a tricky problem. And you know, if you get stuck or tripped up by this, or you pick the wrong one, then you're going to be okay. It's, you know, you're not going to get a 0 for this entire problem. So if we move on to part B over here, we're going to see that getting part A right is not necessarily going to matter for part B. So part B says, a cylinder has mass m, radius r, rotational inertia I about its center axis, rolls without slipping up a ramp that is inclined at an angle theta. Derive an expression for the magnitude of the frictional force exerted on the cylinder by the ramp, expressed in terms of all these things and physical constants. Begin your derivation by writing a fundamental physics principle. So we have to get this friction force going in the right direction in order to get this problem. So if your friction force wasn't going in the right direction, it's not going to be, you're not going to get the right answer to this one. So let me just use this space down here and sort of show you how we're going to figure this out. So once again, we are looking for expression for the magnitude of friction force exerted on the cylinder on the ramp. So what we can do, or we're always going to start out by some sort of fundamental thing. This equals I alpha. So at least you'll get a point for this. So at least you'll get a point for this one by just writing this down. And then let's see what else we're going to get over here. So we can write these things down. So let's draw a diagram over here, mg going down, and then we're going to have a friction force going like this. Oh, that's what I was going to say. So we can also write down some of the forces. Ugh, that was a terrible sigma. Some of the forces is mass times acceleration. So that's nice to do as well. As far as the torques over here goes, there's just one torque, and that's the friction force, and it's acting at a distance r away. So we get friction force times r, and that equals I alpha, and I is something that we can use in our answer, so that's pretty nice. So we're just going to leave that alone for a little bit. Actually, we can do one other thing with it. Friction force times radius is I times A over r. And that's going to help us because we'll be able to figure out something with the acceleration from over here. So let's look at the forces that are acting on this thing. If we look at the forces kind of with a free body diagram, we're going to have an mg sine theta going this way. And then there's that friction force going this way. And that's all we really care about. We have the normal force, of course, going like this, and we've got mg cosine theta going like this. Don't necessarily care about those so much. Might be nice to just draw them in. Fn mg cosine theta. So now in the x direction here, I'm going to pick down the ramp as positive and up the ramp as negative. So I'm going to have, because I know the acceleration is going to be down the ramp. That's why I'm picking it that way. So I'm going to have mg sine theta minus the friction force is ma, because I know my acceleration is going down the ramp. Now from here, I can substitute in this one. So, oops, this shouldn't say times. This should say friction times r equals I A over r. So let's solve this. Let me see. So we're looking for, let's solve this for A. So A is F r squared over I. And then we'll stick that in over there. So let's do mg sine theta, because A is the thing, we don't have A. That's why I'm solving for A here, because A, we're not allowed to use A as one of our terms. So I need to get rid of A in this one. That's why I'm doing that. If I tried to get rid of f, then I would end up with a equals, and I'm not looking for a, I'm looking for what f equals, the friction force. So that's minus this equals m times f r squared over I. Cool, and then we just do a little bit of algebra. Mg sine theta equals, pull the f over there. So, but I'm going to pull this f out. So it's going to be f times 1 plus whatever's left over here, mr squared over I. And then we just put it pull to the other side. So this is going to be not pretty. Mg sine theta over 1 plus mr squared over I. But what I like, is that right? Okay, sure, I guess so. Yeah, if I guess the idea here also is that if my moment of inertia was just mr squared, then I would just get this friction force is just mg sine theta out of it, which seems to make a little bit of sense. Okay, so now we move on to part C. So this is great. Hopefully you can maybe get that. But you know, the rest of the first three problems in this year were really quite easy. So if you stumble a little bit on one of the problems, you're going to be okay. But this is still pretty doable over here. All right, let's move on to question C. In a different scenario, the centers of mass, the original disk and ring, each have the same initial speed as they did in the original scenario. The ramp is replaced by a new ramp in which they initially slip as they roll up the ramp. Ugh, I hate slipping problems. So, okay, indicate whether the magnitude of the kinetic friction force exerted on the disk on the new ramp, the magnitude of the kinetic friction force exerted on the disk on the new ramp is greater than, less than, or equal to the magnitude of the kinetic friction force exerted on the ring on the new ramp. So we're comparing the kinetic friction on the disk to the kinetic friction on the ring. So this is one of those problems where you could just really go off on a tangent and go further than you really need to go. But the idea is, if you have a kinetic friction force, it's just mu k times the normal force. And that's always going to be the case. When you have a static friction force, then it can change a little bit, and you never know what the static friction force is going to be, because it's not always going to be at its maximum value. But when you have a kinetic friction force, then it's always mu k times the normal force. This is the only thing that changes. So if we're comparing the magnitude of the friction force on the disk and the magnitude of the friction force on the ring, they're going to be the same, because they both have the same mu and they both have the same normal force because they have the same mass. And that was weird to think about, because back here, these forces were a little bit different, but these were static friction forces because it wasn't slipping. So when you have a scenario where you have a object that's moving and it's touching a surface and it's not slipping, then when we get up here, the friction force is a static friction force, because these surfaces are momentary, they're not moving relative to each other. But when we have kinetic friction and they're slipping, then it's kind of like all bets are off. They're going to have the same thing. So I would say that they're going to be the same, because Fk only depends on mu and Fn and so forth. Once again, be neater than me and then write that out a little bit better. Okay, that was question 4. A tricky one. Would you have gotten all the points on this one? Maybe, maybe not, but you could have gotten half of them pretty easily.